So this is where we left off, and I just want to talk about this one more time, make sure everything's clear. So we have a graph, and our graph is determined by a t value that's increasing. So when t is small, our x value is going to be small, and our y value is going to be very large, which means that when t is 0, our point's going to start like way up here somewhere. And then as t gets bigger, our x value is going to become bigger, and our y value is going to become smaller. So our point is going to follow a curve that looks like this, which you should have seen in the animation. So now this is the path that the point is taking, but the question is, how quickly is the point moving? And that is determined by x prime t and y prime t. So for x prime t, we determined that when t is small, this is going to be very large, which means x is going to increase quickly. And then y prime t is going to be infinity, but it's going to be negative because it's negative 1 over t squared, which means y is decreasing quickly. Which is why when you hit play on that animation when t is 0, the point just goes like really quickly. You can't even see it follow down this line because of how quickly x is moving this way and how quickly y is moving downwards. And again, if you want to review that animation, it's url.peak2peak.org/d3desmos3. That'll show you the point taking that path. Now, continuing on, when t is larger, x prime t is getting smaller because we can just plug in some kind of large number like 10,000, and we'll see that that value is going to be close to 0, which means the speed of x is approaching 0. So it's still getting bigger, but it's just going to slow down as t gets bigger. And then y is always negative because it's negative 1 over t squared. But when we make t really large, it's going to be 0 and negative, which means that y is decreasing still, but it's going to start decreasing slower and slower. So again, if you hit play, what you see is it goes really quick, and then it just slows down, and as t goes on, it's going to keep slowing and slowing and slowing. If you let it go on for a long, long time, eventually it's going to look like the point is barely moving because of how small x prime and y prime are. So now we're going to move on to talking about ellipses. What I want you to do first is sketch x equals 5 cosine t, y equals 3 sine t. So try to do that by yourself first, and then I will show you. So we have x is going to go to 5 and negative 5, and y is going to go to 3 and negative 3. So then we can draw our ellipse. Okay, that's not bad. So here's our ellipse. And now we want to talk about the slope of the ellipse. So we're going to find dx dt and dy dt. So reviewing trig derivatives, this is a chart that I had you draw back in Unit 7, but we should draw it again. So, and we'll use t this time because t has been our common input, sine of t. The derivative of sine was cosine. The derivative of cosine was negative sine. The derivative of negative sine was negative cosine. And then the derivative of negative cosine goes back to sine. So there was a whole lesson in Unit 7 where we justified these and looked at the graphs to justify these derivatives. And then we drew this chart, and I told you it was okay to just memorize this chart. So then, if we're finding dx dt is 5 cosine t, what's the derivative of cosine? It's negative sine. So x prime, aka dx dt, is going to be negative 5 sine. And then y prime, which is the same as dy dt, okay, what's the derivative of sine? It's cosine, so that's going to be 3 cosine t. So we have negative 5 sine t, 3 cosine t. So next up, find dy dx. See if you can remember back to part 1 of this lesson, how we use dy dt and dx dt to find dy dx. Okay, recall dy dt divided by dx dt. If we divide these fractions, that is going to lead to dy dt times the reciprocal dt dx, which is dy dx, which is the slope. So dy dx is just going to be dy dt divided by dx dt, which is 3 cosine t divided by negative 5 sine t. So this is going to tell us the slope of what ellipse? This one over here. It's going to tell us the slope of this ellipse as time goes on. So let's look a little bit closer at that. Let's look at 0 to pi over 2 because, again, we're going to continue to travel around the unit circle here, right? So the first quadrant would be 0 to pi over 2. So what happens to dy dx from 0 to pi over 2? Well, when t equals 0, 3 cosine 0 is equal to 3, because cosine 0 is 1. Negative 5 sine 0 is 0. So we're going to go from an infinite slope to, well, what happens at pi over 2? 3 cosine pi over 2 is 0. Negative 5 sine pi over 2 is negative 5, because sine pi over 2 is 1. So we go from infinity to 0, which means we're going from a vertical slope to a flat slope. And then what about from pi over 2 to pi? Well, we have 3 cosine of pi over 2 is 0. Negative 5 sine pi over 2 is negative 5. That's the calculation we just did for this one. That's 0. So then what happens at pi now? Well, 3 cosine of pi is negative 1, so that gives us negative 3. Negative 5 sine pi is 0, so that's negative 3 over 0, which is also going to be infinity. So we're going to go from a slope of infinity to a slope of 0, and then a slope of 0 back to a slope of infinity. So we're going to go vertical to flat, and then flat back to vertical, which we can see here. So let's zoom in on this picture before anything else. Okay, we have a vertical slope at t equals 0. Okay, that slope goes from vertical to flat, and then it's going to go flat back to vertical back to flat, and then flat back to vertical. So as we let our t value get bigger and bigger and bigger, it's going to continually go from vertical to flat to vertical to flat back to vertical. So then we can also find our slope at random times, like t equals pi over 4. So 3 cosine pi over 4 over 5 cosine pi over 4. You should recall that those are going to be the cosine pi over 4 are the same. They're both root 2 over 2. So we can just cancel these, which just leaves us with a slope of negative 3/5. So after pi over 4, our slope is negative 3/5. So you can see that this slope is negative, and it's a slope that's smaller than 1, right? So a little bit smaller than 1. It's about negative 0.6. And so we can see that at t equals 0, we have a slope that we have our vertical slope. Then we have t equals pi over 4, which is our slope of negative 3/5. And then up here we have our slope at t equals pi over 2, which is flat. And then the last thing we looked at was that if we go all the way to pi, then we're going to have another vertical slope. So we can find the slope of this curve at any t value by just plugging in to dy dx 3 cosine t and negative 5 sine t. And let's go ahead and look at that animation. Last one, I will link it. You might have been able to guess it's going to be /d3 Desmos 4. So let's talk about what you're seeing on this animation. You have y minus 3 sine a equals negative 3/5 cotangent a times x minus 5 cosine a. So why is that giving us the slope of the ellipse? Well, remember, what is the equation of any line through a certain point? It's y minus y1 equals m times x minus x1. So why is this the line that's going to be tangent to our ellipse 3 sine t, or 5 cosine t, 3 sine t? So, well, our y1 is determined by 3 sine a, right? Y is 3 sine t. Our x1 is determined by 5 cosine t, so 5 cosine a. And then our m value is determined by our dy dx. Our slope is determined by dy dx. So you can recall that cosine over sine is just equal to cotangent. So we should say that cosine over sine is cotangent. So we can just write negative 3/5 cosine over sine as negative 3/5 cotangent. And then a is our slider. A is representing our t value. So as we let our a get bigger, that is going to give us our line that is tangent to our ellipse at x comma y with this slope. So you can hit play and watch as that tangent line goes around and around the circle. And then what I want you to do as well is in your slider, you can just write what you want a to be equal to. So do a equals pi over 2, do a equals pi, and then do a equals pi over, I don't know why I did a capital A all of a sudden there, a equals pi over 4, and just see what that slope is. You should know based on the work we did earlier, but this will just allow you to see it on the picture again.